This is the Chapter 8 handout. This can be found under the Handouts tab in Blackboard, but I just want to explain what we're working with here. So when we're testing the population mean, like we did in 8.1 and 8.2, there's two things that we use depending on whether or not we know sigma. So I just want to make it clear that if we're testing the population mean, we're up here. If instead we're testing the population proportion, we're over here. And now this here, testing paired differences, that's from a section that we're not going to cover. So this is from 8.5. So this you can completely ignore. We're not going to cover that. So we are always going to be testing either the population mean or the population proportion. So one thing to notice, if we're testing the population proportion, there's no question we always use standard normal distribution, and we're going to get a z-score. If we're testing population mean, then it depends. If we know sigma, we are going to use standard normal distribution and a z-score. But if sigma is unknown, like we first saw in section 8.2, if sigma is unknown, then we use student's t-distribution and a t-score. So we use z here and we use z here, and the only time we ever use a t-score is when we are looking for the mean, we're testing the mean, and we don't know sigma. All right, so I just want to make it really clear, because whenever there's a proportion involved, it's always a z-score, just like in section 7.3. Now, one thing that is different with 8.3 is, if you remember in section 7.3, we didn't know p. We were actually trying to find it. In 8.3, we will actually know p because p comes from the null hypothesis. So that's the only difference. But other than that, 8.3 or chapter 8 follows chapter 7 pretty closely. Then normally in class I do this little experiment where we talk about the p-value using a coin flip. I'm going to post a video. There's this video called Stories of Statistics. It was a math seminar video from a few years ago. It was a video that I had, or a math seminar that I had done. And if you look on that it's a YouTube video from this time to this time in the video, this experiment that I do in class is done on that video. So I'm going to show a little clip from that video. And if you want to see the rest of it, if you go to the grcc.edu from the homepage and go to the math department, you can go to the math seminars link, and there's a bunch of math seminars there. But this is the part that I wanted to show, is when we talk about the p-value using a coin flip. Which leads us to, what is a p-value? And this is something that these are just using all kinds of fields of science, especially in the social sciences. And I want us to just look at any research paper. A lot of them will say something about p-value was this. P-value was this. And I just want us to, when we leave, just kind of have a good intuition about a p-value. And I think there's an easy way to get that intuition, which we'll do right now. So a p-value is a probability. You can think of this p just meaning probability. The probability of getting a result equal to more extreme than it was actually observed, assuming that the null hypothesis is true. That's not going to make much sense until we actually do. We're going to do a quick experiment here. So it turns out the smaller the p-value, the stronger the evidence against the null hypothesis. So what we can do is we can test a coin toss. So let's say we've got an outcome p-value. So this one, let's say I've got a null hypothesis. Let's say I've got a quarter. So the null hypothesis is the coin is fair. The alternate hypothesis is the coin is not fair. Meaning it's got a 50-50 chance of landing heads or tails. So let's see if I can do this without dropping this all over the place. So let's say I flip this coin. Heads. Okay, so the outcome is heads. The p-value is the probability that I could get this, given that this is true. If I have a fair coin, what's the probability that I would get heads? 50%, right? The p-value is just a probability I could get this outcome, given that this is true. That's a p-value. Okay, so let's do it again. So I have a head now. Heads again. So what is the probability that I could get this outcome, given that that is true? Now what's the probability? 1/4, right? We use the multiplication principle, right? Because these are independent events. Like, if I get a head, it doesn't have any influence on the next coin flip, right? So now I've got 1/4, or for the decimal fans out there. Okay, let's try this again. Okay, is everybody ready to say, oh, I think it's definitely not, it's definitely not real. Something's wrong here. So now I've got 1/2 times 1/2 times 1/2. I've got 1/8, right? Anybody ready to say I don't think that's a fair coin? Not yet? Not yet, okay. So you guys looking a little skeptical, but not quite yet. Okay? Oh, wait, that's a bad one.
Heads.
Heads again. That's 1/16, 0.0625. So remember what this is. The p-value is a probability we could get this outcome given that this is true. That's the p-value, right? Okay. Anybody ready to say, wait a minute, something's not right with that coin? Okay. Yeah. So what will happen? We could have a distribution. We could have a probability distribution that counts the number of heads. So one of them would say, like, what's the probability we get? All heads out of, like, 4 heads out of 4. So I think of it like 4 heads out of 4. So let's try one more.
Still heads.
Still heads. Okay. So we have 5 in a row. Usually about at this point, wait, 0. What is this? 1, 2, 5. So usually there's usually a cutoff point where these p-values, where people right around here start saying, wait a second, something's funny about this. So it turns out, usually around here, if the p-value gets to be less than 0.05, that's when usually people say, well, if there's a 5% chance of this thing happening and it just happened, maybe this isn't quite right. How many of you guys think, okay, let's take a vote. Who says you're ready to reject the null hypothesis? Who's not? Who says let's do it one more time? Okay, so see, we're about at the cutoff point. It's usually in a published result, they'll start off with this. Sometimes it's 0.01. But all the p-value is a probability that you got your outcome given that this is true. That's all it is. So if we make a probability distribution for 10 coin flips, all this is the probability that, and in this case, if you have 10 coin flips, on average, you could think, well, I'll probably get 5 heads, right? That'd be the peak value. Now, every once in a while, if you flip 10 coins repeatedly over and over and over, every once in a while, you get like 9 heads, right, out of 10. Not very often, which is small. In case you're wondering, to save the suspense, the alternate hypothesis was true in that case. This is a two-headed quarter. Remember one thing, though. At the end of that experiment, we looked and saw that it was actually a two-headed quarter, so we knew the alternate hypothesis was true. In reality, we never know if we're right. So remember, we're usually going to be right, but of course, we never know for sure. And another thing that I typically do in class is I pass around some research papers, and this is a couple of pages from them, so maybe you can zoom in on these and look. But the thing that I want you to notice is there are p-values mentioned all over the place. So you can see I highlighted some of the things that we talk about in class, about statistical significance and p-values. There's some here, there's some here. This is a paper that was actually, the research was actually done at our college. So just so you can see that the p-values are mentioned all over the place in research. And here's another one. Again, this one was also some research that was done at the college. And again, you can see that they mention, let's see, in this case, alpha level, and there's a bunch of p-values. This is either using a t-test here. This is an f-test, which we may talk about depending on how much time we have. But a lot of, again, a lot of p-values. And there's more pages to these papers I'm showing you too. I'm just trying to show you a couple of pages so you can see that these p-values are all over the place. And then this is another one. This was some research involving cancer. And again, you can see that there are p-values mentioned. So they mentioned these statistically significant p-values. This one used SAS, which is a software package I had mentioned at one time or another. So whenever you look at research, p-values are used all over the place, which has led to some criticism of p-values because sometimes we are too dependent on them and assign too much weight to a p-value. So I had mentioned that p-values are coming under some criticism, and it's because a lot of times publishers won't publish a paper unless you have found something that is statistically significant. In other words, you have a p-value of 0.05. And the problem with that is that means that when you are studying something and maybe you have shown that there is no relationship between a couple of variables, well, if that was to be published, people would get that information and they would have that information available for other research. But instead, you only are able to publish things that have shown that there is some sort of relationship between a couple of variables. Or in other words, you've got a p-value of 0.05. So you end up introducing bias into research that is available. But not only that, with today we have access to so much data that you get this situation right here. And this is 538 shows this example. And if you Google 538 p-hacking, you can find it. But they have a bunch of data and they allow you to choose these categories over here. And you can pick a political party, and by picking various combinations of data, you can achieve a publishable result. So right here, if I choose these categories here so that the data under these categories is all compiled, you can show that Republicans have a positive effect on the economy. So you could publish this paper and you could go on Fox News right? Because you cherry picked your data to get a result that had a p-value of, in this case, less than 0.01. Okay, so now if you change this a little differently, like in this case over here, this one is, I just changed, look at the categories here. The categories are a little different, right? Instead of using these categories, I use these categories. Now look at this. Now you can show that Republicans have a negative effect on the economy. So now you can go on CNN. So it shows that by cherry picking your data, you can get a p-value of pretty much whatever you want, which is why you're supposed to have your data first, right? And then you have your level significance alpha, and you have that before you start compiling the data. Then you compile the data and let the data stand where they may, figure out the p-value you have, and go from there. So that's the problem. There's some pressure, especially in places where you have a lot of pressure to publish papers. Then that means you need to find these p-values of 0.05 so that your paper becomes publishable. So this is becoming a problem. It's even got a name, p-hacking. P-hacking is just tweaking your data so that you get something that's publishable. And it's a problem because with so much data available, you can pretty much find evidence for whatever pet theory you have. So it is a problem, and it's just something that you need to be aware of. And then the last thing I have is something for Valentine's Day. When it's coming next time, here's a little poem you can use. Okay, you're going to want to write this one down. Say, roses are red, violets are blue. Okay, here's where it gets really good. If you were a null hypothesis, now you ready? I'd fail to reject you. So there you have it. A little something special for date night. And don't forget, at the end, always put one of these. I'll put it in red. The color of love, right? Remember what that means. TLA, true love always. Okay, so hope that helps, and let me know if you have any questions.